Section 9.5, rotational work and energy. So now we're continuing this idea of coming full circle to the ideas that we've looked at previously, and we want to find the rotational equivalent of all these linear things that we've seen. So work, for instance, we calculated with F times S, the force times the displacement S, assuming they're in the same direction. But S, if we're thinking now of rotation, S could be described as the arc length, that distance on the outer rim of an object. That's what's shown here, where the wheel is rotating by some amount as the rope pulls on it, and the amount that it rotates matches the arc length. Arc length, we know how to calculate in terms of our angular variables, right? It's equal to the radius, the size of the wheel or the round object, times theta, the angular displacement. So we'll put that in for our S, that it is the displacement in the work is r times theta. What about the force? We again want to get the angular or rotational equivalent. So if we have force that's causing a rotation, we can think of that as torque. Torque is just force times the lever arm, where the lever arm is the distance from the axis of rotation to where the force is being applied on the line of action. Since the force is being applied tangentially, it's just the radius r. So we can put in that the force is equal to the torque tau divided by r. That will cancel out the r's, and we find that the work is just the torque times the angular displacement. So to pull this all together, our definition of rotational work is that the work done by a constant torque in turning an object through some angle theta is given by the torque, whatever that constant torque is, times the angle that you've turned through. So that allows you to calculate the work done. Awesome. Note the requirement here is that the angle must be in radians. So once again, we have to be in our SI units of radians. So make sure that it is in radians, or else you will not get the correct answer. It just won't work. The SI unit of rotational work, if we take torque is Newton meters, and we multiply by radians, which are basically dimensionless, you might say we stick with Newton meters, but once we switch to talking about work or energy, we instead are going to, instead of calling it Newton meters, we're going to shift to our energy unit or our work unit, which is what? Joules! So it's a little bit funny, but by multiplying by that angle, we now will describe it as joules, as energy or as work. Speaking of energy though, we should talk about energy too. All right, so kinetic energy, we previously looked at for the translational case, right? For objects that are moving without rotating. We saw that it was equal to 1/2 the mass times the tangential speed squared. But that tangential speed, we know we can relate to our angular variables, and that our angular velocity times the radius is equal to the tangential speed. So we'll plug those in. So it's 1/2 mr squared times omega squared. This is what it would be for a single object that is rotating, right? That is traveling around in a circle. What if we want it to be a full rigid object, like something spinning on a point, like they show this disk here that is rotating? Well, then we need to consider the contributions of a bunch of masses, all the little masses that are at various distances. So once again, we would go to a summation notation. We would sum up the 1/2 mr squared omega squared, the kinetic energy contribution of each of these point masses. And what we'd find is that all of these have the same angular velocity. The angular velocity is constant for the entire object. No matter how far you are from the axis of rotation, angular velocity stays the same. So that we could pull out of the summation. The 1/2 also would be the same, so that we could pull out of the summation. And notice in parentheses, we have the sum of mr squared. That's just our moment of inertia, I. So we get this rotational equivalent of kinetic energy instead of being 1/2 mv squared, we have 1/2 I omega squared. Pulling this all together, our official definition of rotational kinetic energy is that for a rigid rotating object, it's 1/2 the moment of inertia I times an angular speed squared. This is a really useful equation. It happens anytime something's rotating. So we have it as Ke subscript r to note that it's rotating. Once again, our angular speed needs to be in SI units of radians per second. That's the only way that this works out. And the unit that we will get when all of this is said and done is going to come out to what? Well, because it's energy, it's joules. So you got to say it with energy. Otherwise, it's not really energy, right? This is how we can then calculate the kinetic energy that goes into an object that is rotating, as well as the work done in rotating an object when you have a constant torque acting on it. So this concludes section 9.5, rotational work and energy.